Hello and welcome. I'm Steve McQuerry, and I work in the FlashArray platform team, which is responsible for hardware architecture here at Pure Storage. Many of the benefits that our customers enjoy, from simplified operations to painless controller upgrades, can be traced directly to innovations in Pure's hardware and software architecture. In this session, we're going to dive right into those key architectural elements to help you better understand and get more value from your FlashArray systems.
And I'm Van Phan, and I work on the software side of the FlashArray, and I'll be digging into the FlashArray's software innovations that are a crucial part of the peer user's experience. But first, let's start with some of the core parts of the FlashArray's hardware architecture that even a decade after development remain a unique part of the data storage industry. Steve, I understand that the data path for the FlashArray's dual controllers and the fact that the controllers are stateless are key differentiators. Could you tell us a little bit about that, and starting with maybe the active-active controller design?
Sure, Van. One of the key strengths of the hardware design for FlashArray is the dual stateless controller design. This dates all the way back to the beginning before we started building our own hardware. In those days, we relied on InfiniBand RDMA connections between the controllers to pass state information and I/O, and dual SAS paths to provide both controllers access to a common storage media. Now we accomplish the state path via a PCIe non-transparent bridge or NTB connection between the primary and secondary controllers within the chassis. The media connectivity to both controllers is accomplished in the chassis by providing both PCIe and SAS paths. In this design, both controllers are able to service I/O to and from the SAN ports, but only the primary controller is responsible for the back-end I/O services. The advantage of this design is that we can easily change which controller is active without disruption to the application.
That's cool. I know that NDU is a big part of why customers love Pure, and I understand that both controllers provide symmetric active-active access to your host, even though only one controller is processing I/O at a time. But how does the fact that the controllers are stateless fit into this?
One of the fundamental decisions we made a decade ago was to abstract all of the state information out of the controller hardware and into a database that's synchronized between both controllers. This makes it possible not only to swap out a failed controller non-disruptively, but even replace it with a whole new generation of controller. The secondary controller constantly monitors all of the information required to main state. This happens across a high-speed NTB link between the controllers. Any messages regarding state information that go to the primary are received by the secondary at the same time and copied into memory on that controller. Essentially, the secondary has two jobs: pass host I/O to and from the primary and take over the state in the event that the primary is no longer available. This lets us take one controller at a time offline for software or hardware updates without compromising performance. As an example, during a code upgrade, we will take the secondary offline so that it is no longer processing I/O to the host. We can then upgrade the code and restart the controller. Now that it is running the new code, we will promote it to primary and take the primary offline. With the old primary offline, we can upgrade its code and then restart it as secondary where it'll start processing I/O again. Of course, FlashArray's innovative architecture is about software as much as hardware, starting with the way we approach data reduction. Ben, can you tell us a little about that?
Sure, Steve. Data reduction has been a key differentiator for Pure from day one. We don't just do a simple pass to dedupe and compress the data at one time. We actually perform data reduction at multiple different layers, and that includes inline compression, inline dedupe, pattern removal, deep compression, and deep dedupe. By the way, we have 4 compression algorithms which are dynamically driven by our AI and machine learning technology. So let's take a look at an example here. So we have a 512K sample data set filled with different types of data. So the first thing we'll do when the FlashArray receives this is it'll lop off the end of the data set if it's filled with a bunch of zeros. So that's basically thin provisioning, right? Any volume on the FlashArray is pretty much thin provisioned by default. So if you create a LUN or hundreds of LUNs, nothing gets consumed on the back end until you actually mount it and write data to that LUN. And then the next thing we do is go ahead and remove any patterns or scattered zeros throughout the data set. So a pattern basically is any sector with a bunch of repeating 1 byte patterns within that sector. So if we sense that, we'll just eliminate all of it and just store one copy of that and then have pointers back to that 1 byte sector if it's ever needed to be read. And then next thing we do is we perform the inline dedupe. So any blocks that have been written already, we'll compare the hashes for it, and decide whether they exist or not. And if it does, we just don't write it to the back end. We just use our pointers and metadata to show that they already exist. And then the last part of this inline data reduction process is the fact that we take any leftover unique data and then we compress that down to a smaller footprint. So then you'll have a much smaller footprint overall with your data set during this inline process. But hold on, we're not just done there. We continue to reduce the data afterwards as well. So this is just showing the inline process, but we'll get into a little bit of the back end on the deeper data reduction and how we actually do it as well. So now let's take a closer look at our inline dedup. So what we have here is our streaming data coming in. And first we look at a 512 kbyte sample, and that's the window that we use to look at our dedup. So we generate a hash out of this sample. In this case, the hash value is H421, and we compare that to our dedup table that's sitting in memory. So if there's if the data does exist, then we'll see that it's a hit and we don't have to write that data. But if it's a miss, it means the data is unique, and then we end up writing that into the dedup table. And then we'll keep going and we'll slide that sample size to the next block over, and then we'll create another hash here. So in this case, the hash is H552, and it does not exist, so we enter that into our table and we'll move on. Sliding down to our next sector, we have H327. That is a miss, so we'll enter that into the dedup table and move on. To the next one, we have H916, again another miss, so we'll just enter that into the table and move on again. And this next one happens to be a hit. H986 is in our dedup table, so we know the data exists already, so we end up not having to write that piece of data. And then we continue on with this actually. So this is another step after we get that first hit. The next thing we do is actually compare that data to ensure that it's 100% a match. So there's no mistake at all, right? We take a bit for bit comparison and truly confirm that that data does exist. And once we do that, we do something else that's pretty cool, is that we now check the adjacent sectors as well. So we'll go ahead and expand the adjacent sectors to see if there's any additional matches as well. So we'll go ahead on either end, check the sectors until there's a miss on each end. So this is just one of several reasons that make our data reduction so spectacular compared to other vendors who have fixed block sizes. We have variable block sizes that dynamically change to squeeze out as much duplicate data as possible. The next thing I want to do is go through our compression implementation and compare that to how other vendors do it. So let's start with other vendors. Typically, when other vendors get IOs, they, let's say for example, get a 16K IO from the host, and they use one single algorithm, right? So in this case, let's say the algorithm goes in and reduces it down from 16K to 13K. However, most vendors use fixed block sizes. So even though you have 13K of reduced data, you're still using a block size, in this case of 16K. So you have 3K of wasted space, and that space can't be used for anything else. Therefore, technically, you really didn't save anything. The other option that the vendor can do is take that 16K and break it down to smaller fixed sizes. So instead of one large 16K block, they break it down to, say, maybe an 8K block, a 4K block, and a 2K block. But now you have 3 individual backend IOs instead of one IO. So that's one issue that other vendors face. Now, what if they go in and say take a 16K IO and was able to reduce it down to say 7K of actual data or data that needs to be written? In this case, you still have a wasted 1K worth of space, even though your data reduction was much better with this one single algorithm. So then after that, when you have a lot of these IOs that come in, you end up just overall getting a lot of sparse white space that is wasted overall. So you end up just you're not being very efficient, even though you have maybe a decent algorithm for compression. So now how do we compare that to pure storage? So we differentiate ourselves with two main ideas here. We actually use AI and machine learning for our compression algorithm. and we use variable block sizes to pack it down so we have less wasted space. So for example, let's use the same exact data set that we were showing with the other vendors. Now, when an IO comes in from the host, we use AI and machine learning to decide which algorithm out of the four that we have will be the best one to compress down the data. So we slowly learn over time, and after we learn and decide that host A with an 8K IO has the best results using algorithm B, then we'll continue doing that and we'll continue learning as we go along for other block sizes of IO. And then over time, we continue to relearn and optimize those results. So this is a really big differentiator when you compare to other vendors who may only standardize on one algorithm, right? We actually have four to choose from, and we can choose the one that yields the best results depending on the host and depending on the data set. So to round off the comparison here, for the same exact 104K of host written data, we're able to reduce it down to 44K of allocated on the back end, which gives us a 2.36 to 1 compression ratio, as opposed to other vendors who, because of the fixed block sizing and the single compression algorithm, can likely just do something around the 1.3 to 1 compression with about 12K of wasted space. Now let's go back to you, Steve. I know that software-driven data efficiency is a big part of Pure's performance advantage in the marketplace, but that NVMe is a big factor as well on the hardware side. Can you tell us a little bit about that?
NVMe is the game changer when it comes to accessing flash media. One of the great things about flash is that the technology is not inhibited by the basic mechanical structures of spinning media. There's no spinning drive, there's no disk head to go back and forth. But when flash first came to market, the interface protocol that we relied on was based on the SAS and SATA technology, which was developed for spinning media. Didn't take long for the industry to figure out that flash could access data much more efficiently than a spinning drive. So the NVMe work group was formed to develop a new protocol standard. NVMe as a standard provides more queues and a higher queue depth, which allow data to be served faster by accessing it simultaneously. It also provides a mechanism to communicate directly to the CPU using PCIe instead of a controller that's connected to a PCIe bus. Pure is a member of the NVMe workgroup, and we embraced the NVMe technology early on in our design. Starting in 2015 in our NVRAM technology used to accelerate writes, then again in 2017 in our direct flash module, which is an NVMe flash module. You may recall that I mentioned our chassis has both SAS and PCIe paths between the controller and the drive bays. The chassis was built so that as native NVMe drives became available, customers would be able to upgrade without changing out the chassis. This has allowed our customers to upgrade from SAS-based FlashArray M to an all-NVMe FlashArray X without incurring any downtime or having to migrate data to a new platform and pull out the old one. In 2018, we introduced the Direct Flash Shelf, which leverages NVMe over Fabric to add additional capacity and maintain the efficiencies of the NVMe protocol. And in 2019, we enabled NVMe over Fabric to the host with the introduction of Direct Flash Fabric to provide an end-to-end NVMe experience. The architecture makes it easy for our customers to upgrade and modernize their environment. And as you know, Van, easy is one of the driving principles in all of our design considerations.
Okay, thanks, Steve, for that detailed explanation. So now this is the end of our session. I want to thank you for virtually joining Steve and I on this deep dive. I know it's a bit unorthodox compared to our really cool live events in the past, but hopefully we'll be able to move past this together and be physically together next year. Thanks again.